Okay, so last time we talked about some analysis for the Frankfurt and the projective gradient methods. So one thing that I want to talk about is this projection theorem. So if you have a closed convex set and can you guys just keep quiet? If you have a closed convex set and for any point x, and fc is the projection of the point onto the convex set C, so we have the following characterization. So basically, if you pick n in z in this set C, and then this inequality holds. Okay, so x minus xc is negatively correlated with z minus xc. So this is the point, and this is the projection. This vector is negatively correlated with any of this vector. Well, this z can be any point in this set. Okay, and this is a very useful result because it is a necessary and sufficient condition for the projection point fc. So it and in fact, such a projection point is unique. It can be shown that. Now, this is a very useful result that can be used to prove the non-expansiveness of the projections that we showed last time. So this result says that once you project a point onto a convex set, the distance is going to be smaller. And there's a very simple proof that we can find on the web page. This is the characterization of the projection of onto convex sets. Z1 is any point, right? PZ1 is the projection point. And then the result says that for any x in the convex set, these two vectors are negatively correlated. This holds for any x. Now, in particular, we can replace x by a projection onto Z2. Well, Z2 is any other arbitrary point, right? And PZ2 is the projection of Z2 onto C. Okay, so this point must be in C. So we just replace x by this P2. And similarly, we can just swap Z1 and Z2, because Z1 and Z2, they are just two arbitrary points. So we can swap this Z1 and Z2, and then we get the same inequality, but with Z1 and Z2 switched. Okay. And then we add up these two inequalities, we can get this inequality. Right. This one says that PZ2 minus Z2 in the product with PZ2 minus PZ1 is less than or equal to 0. Well, these Z1 and Z2 are arbitrary points. And then, okay, and then this inequality, okay, this inequality is equivalent to the following inequality. So you can check by rearrange, by merging the left-hand side with the right-hand side. Okay, they will reduce to this inequality. So this is just the expansion of this one to this one. And on the left-hand side, it is actually PZ2 minus PZ1 in a product with itself. So on the left-hand side, it is basically the PZ2 minus PZ1, the distance to the power of 2. On the right-hand side is the Z2 minus Z1 in a product with PZ2 minus PZ1. Okay. So the left-hand side becomes a squared distance. Okay. And the right-hand side is a dot product. This dot product can be bounded by the product of the norm by using Cauchy-Schwarz inequality. Right. So just combining, just move this part to this inequality. We have square distance less than equal to product of this distance, and then we cancel one of them. We can get this desired result. Okay. This proves that the projection onto convex set is a non-expansive operation. Okay. So we start from this characterization of projection onto convex set result. This is a sufficient and a necessary condition. And then we last time we talked about the convergence rate of projective gradient descent for solving convex and smooth constraint problems. The convergence analysis is a direct generalization of the analysis in the unconstrained case. Okay. Where we basically replace all the gradients by the so-called generalized gradient. But a fundamental key result that we want to prove is the following result. Okay. This result shows that for any x and y in the constraint set, and define x plus as the one step projective gradient descent applied to x. This is like starting from x and apply one step projective gradient descent. And GCX as x minus x plus. This is the generalized gradient that we defined. Then for any x and y in the constraint set C, and the x plus and GCX, this inequality holds for this inequality holds when f is convex and smooth. Okay. And the proof, the convergence analysis is basically utilizing this inequality in different ways. Yeah, it's just a set x and y, two different parameters, and then we can get different inequalities. Okay. So the key result is to prove this lambda, this general lambda. And the proof is takes several steps, but this is relatively simple. So we start from fy minus fx plus. This is the left-hand side of the inequality. If you move this term to the left-hand side. So we start from this term, and then we add fx and subtract fx. So these two will cancel out, but we introduce them here. After this, we will have two terms of difference. Okay, this is fy minus fx. This is fx plus minus fx. For the first difference term, we will lower bound it using convexity. Right, so this fy minus fx is bigger than or equal to this dot product by convexity. And for the second difference term, we will upper bound them using smoothness of the function. Right, and because this is less than or equal to, but because of the negative sign, it becomes greater than or equal to. So this is compatible. So one term we apply convexity, the other one we apply smoothness. Okay. And then these two dot product terms can be combined together. Okay. Combine them together, we have this one. the x will cancel out. These two terms cancel out. Okay. So combine these two, we have this inner product term minus the quadratic term. Okay. And then before we have one result says that this inner product term is lower bounded by replacing the gradient by the generalized gradient. Okay, this is by the previous 3.6. So using that result, we can get this lower bound. Okay. And for this one, we further introduce an additional term. So we add an x and minus an x. Right, so and then these two can be separated into two terms. This is y minus x and x minus x plus. Okay, just divided into two terms, nothing else. And then it can be observed that x minus x plus, by definition, it is 1 over L times GCX. This is how we define GCX. Okay. So with this observation, this inner product term is basically GCX transpose GCX. So it's GCX to take the norm to the power of 2. And there's 1 over L in front of it. I think it, right.
I have a question.
Yeah.
Yeah, why we call GC is the generalized gradient? Because by fact 3.6, it is it characterizes the projection. I see.
Yes, 3.6 is about the replacing this gradient by the GCX, right? GCX, we call it generalized gradient because it is just because we can write projected gradient descent, right, using this notation. And then the update rule looks like exactly like the gradient descent update. Yeah, so basically x minus x plus, these two difference terms, they are directly equal to 1 over L times GCX. So you plug it in, and the last two terms can be combined together. Just after calculation, the last two terms, these two terms combined together gives 1 over 2L GCX L2 norm to the power of 2. Here we have something, the GCX norm to the power of 2. This one, this inner product is GCX dot product with itself. So it also gives something square to the power, some norm to the power of 2, right? So these two can be combined together. And the resulting term is the positive distance there. And this proves that lemma. This is exactly that lemma. It holds for any x and y, and also the corresponding x plus and GCX. And then last time we showed that how to leverage this general result to prove the convergence rate. The idea is basically set x and y to different parameters in that lemma, and then we will end up with different inequalities. If we choose x and y to be xt, then we will obtain we will bound the progress between on the objective function value between two consecutive iterations. And in step 2, we set x to be xt and y to be x star. We will get a bound on fxt plus 1 and fx star. Okay. And from here, we can get an estimate on the gradient norm, the generalized the norm of GCX. And then combining step 1 and step 2, we can get such a recursion in step 3. Okay. And this recursion can imply the convergence result. Okay, so this is the general proof logic. So in the end, we showed that if F is convex and L smooth, and it's a constraint problem, if we choose such a step size and then the projected gradient descent, this algorithm will converge at such a convergence rate. Okay. It's roughly 1 over t, roughly 1 over t. So this is to summarize the 2 algorithms that we introduced. One is Frank-Wolf, one is a projected gradient descent. For the Frank-Wolf algorithm, we have shown that for convex and smooth problems, if we choose such a step size, the convergence rate is about 1 over t. And the iteration complexity is 1 over epsilon if we want to achieve an epsilon accuracy. Otherwise, moreover, for projected gradient descent, we have 2 results. One is for convex and smooth problems. We choose this step size, and the convergence rate is the same. It's 1 over t and same iteration complexity. But if we further have strong convexity, then the convergence rate can be improved to a geometric convergence rate. So this is much faster. And the complexity becomes log 1 over epsilon. So the complexity is much smaller for strongly convex problems. Okay, so this is everything for the lecture 2, where we focus on optimization problems with convex constraints, convex optimization problems with convex constraints. And now I think you can start working on homework 3. So homework 2 is about apply gradient descent to solve a least square problem. Now homework 3 is actually about apply gradient descent. Okay, there's no constraint. Apply gradient descent to solve a logistic regression problem or using a real data. And basically, this is a brief introduction of the logistic model, and this is the optimization problem, associated optimization problem. This is the cross entropy loss. Now, you will see a data sample. This is a data sample that we will use. This Framingham clean.csv. This CSV file is basically like an Excel. If you open it, you will see. Maybe I can open it here. Yeah, so this is something like this. Yeah, so each row is one patient. Each row is a patient. We have about, I don't know, so maybe thousands of patients, but you can just select maybe a subset of them for training and some other for testing. But you can see each row is a patient. These are the features, right? Male, this is gender, age, education. These are the features. I guess these are related to some medical features. I don't know, like heart rate. Right, up to here, these are the features. The last column is the label. Is a label. 0 and 1 means I forgot the meaning, but I think they indicate some medical. Maybe it's like within 10 years, after 10 years, will this patient die or not? Something like that. Right, so the last column is a binary label. The previous are the related features, and we will. The goal is to build a logistic regression model to predict the label given the features. So the background is you can just read this background file. So data set is given a set of labeled data samples. Xi is the features. It's a vector. Each Xi is a vector of features. Yi is a binary label. So Xi is a vector in RD. And Yi is a binary corresponding binary label. Okay. This is for the I sample. Now suppose we have 1 to n, we have n samples. We want to build a logistic model to predict the label from the features. Basically, the model will do the following. Given the features Xi and some parameters of the model, this omega and b are the parameters that we need to learn, we need to optimize. Given these, given the model, given the features, we want to build a model that can predict the label Y for us. And we will parameterize such a conditional probability using the logistic model. Right? So this conditional probability is Pyi given Xi, and also given this the parameters of the model. And this is how the model works. So suppose given Xi and the parameters W and B, it will calculate this H. This H WBXI is defined as follows. It's 1 over 1 plus exponential negative W transpose Xi plus B. Okay. In the end, this will give us a number between 0 and 1. Now, this is a number between 0 and 1 because exponential is positive. This number will be interpreted as the probability that Yi equals to 1 given such a feature. Okay. So here W and B are the parameters of the model, and the above model, yeah, and we need to learn this W and B in a given data set. And the above model can be equivalently written in this way. You can check this by yourself. Pyi given Xi is H to the power of Yi and 1 minus H to the power of 1 minus Yi. Because Yi is just binary. If Yi equals to 1, it just equals to the reduces to this equation. And then we can follow the maximum log likelihood criterion that we talk about in lecture 0. And that maximum log likelihood framework will lead to the following optimization problem, which is the logistic regression problem. So the optimization problem is this. We want to find a model parameter W and B so that the following loss function is minimized. And the loss function is is averaged over these n samples, right? So it's 1 over n sum from I from 1 to n. This is like a sample average, this part. And the negative, the entire part is the loss function. It's called cross entropy loss. Okay. So you can see from this function that if we are given a set of labeled samples, x, y, and yi, we can plug them in, and then this will define such a loss function over W and B. And we minimize over W and B. Once we solve this problem, the obtained W and B is our model parameters. And we will just apply gradient descent to solve this problem. And here I already give you the gradient formula for this so gradient of f with regard to omega and the gradient of f with regard to b. Okay, both are given. So you follow this gradient update rule and do gradient descent. Okay. And there are some data pre-processing steps that you can follow to normalize the features. Okay, I think you can just check it by yourself. And you will divide the entire data set. Like here, I guess there are 3,000 data samples. Maybe you can split them into a training set and a testing set, right? For example, you can reserve the last 1,000 samples for testing, and then the first 2,600 samples for training. Okay. For the training set, so you will train this model on the training set. Once you apply gradient descent to solve the training problem, right, and once you obtain a W and B, you can predict the labels of the samples in the testing set using the logistic model that you just created. Okay. So you apply gradient descent on the training set to solve the problem. Once you have your W and B, this is how you do the prediction for your testing samples. Now, given your W and B, given a feature, this is a feature, maybe you pick one patient in your testing samples, right? And X is the features of that patient. And then you just calculate this HWBX is the probability that you will predict 1. And otherwise, 1 minus this one is the probability that you will predict 0. Okay. Then the predicted level is set to be the one with the higher predicted probability. So you just look at these two probabilities, whichever is higher, you just assign that label, right? For example, this is higher than this one, then you will just predict label 1. Okay? Then you can do this one by one for the testing samples. Okay. And consequently, you can have you can calculate the testing error. You can compare your predicted labels for the testing samples with their underlying true labels. See how many labels you can correctly predict. So that would be the testing error. The other would be the training loss. Yeah. So this is another application of gradient descent. Lecture 1, gradient descent. But the application is a binary classification problem. Well, homework 2 is about the regression problem, the least square regression problem. Okay. So this is about homework 3. You should be able to finish it. And I will set a deadline sometime next week, maybe. Okay, any questions? This is homework 3. And next we'll get into lecture 3 and talk about subgradient methods. Okay. And it sounds like this is the relaxation of the gradient method, okay? Because it relies on subgradient, not gradient. So we will first look at the motivation. In the previous lectures, we talked about gradient descent, projective gradient descent, okay, Frankfurt. Now these algorithms are to solve convex unconstrained problems or convex constrained problems, but they have a requirement. They require that the objective function f is differentiable. Okay, so we always assume that it is differentiable, so we can compute the gradient. But in many cases, in many examples, we may not have differentiable objective function. So the f may not necessarily be differentiable. We will see some examples. L1 nuclear norm minimization. These are very important examples in signal processing and statistics, and they are not differentiable at some points. And in these cases, those methods simply do not apply. So we want to generalize the previous idea, the previous gradient-based algorithm framework to work for the non-differentiable cases. Again, our algorithm design is still following such a very simple update rule. Every time xt is a step size eta times a search direction or update direction dt. And in the previous algorithms that we discussed, this dt is in most cases is the negative gradient. But when the function is not differentiable, we need to think about some surrogate notions of gradient. And there's a very simple example. This is a two-dimensional optimization problem, and it is convex. Well, when you start from an initial point, when you start from this point and use an exact line search algorithm, okay, and we did not introduce this algorithm, but it is kind of like searching for a steepest descent direction and search for a proper step size. But if we do a line search, this algorithm will get stuck at a suboptimal point. So this xt will goes to the original point, 0, 0. So it will get stuck around a non-optimal point, 0, 0. 0, 0 is not the minimum point. So this implies that if we follow steepest descent, sometimes we may get stuck at a non-optimal point. And the projective gradient descent is a popular algorithm for solving a class of non-differentiable problems, and it is based on the concept of subgradient, or I mean subgradient descent. It's a subgradient-based method. Basically, the update rule looks exactly the same as projective gradient descent, except that this update GT is now a subgradient of function. But in the projective gradient descent, GT is the gradient. But that only happens when the function is differentiable. So we will spend some time on this concept, on introducing this subgradient concept for non-differentiable functions. Okay. And subgradient is a generalized gradient when the function is non-differentiable, right? If you look at this function, at some point, it is not differentiable because there's a sharp. It's like a joint point of two line segments, right? So it is not differentiable. It is not a curve. But you can sort of find the same idea of derivative. Right? If we have a curve, differentiable curve, then we can easily draw a supporting line at that crossing that point. And we say this, the slope of this line, we call this the gradient or the derivative. Right? And because this is a curve, so every point we can only find exactly one supporting line. But when the function, right, has a sharp transition, like here, it is not differentiable because you don't have a proper definition of derivative there. But you can sort of find a bunch of different lines that supports the entire graph of the function. Right? These are all proper lines that supports the entire function. So we call these, we collect all the slopes of these lines. We call them the subdifferential of this function at this point. Okay. So that is the intuition, right? You just, at that point, you can, if you can find multiple supporting hyperplanes of the function, then the slope of those hyperplanes, we call them the subgradient. So subgradient is a set. It is not a single element. It is a set. Like here, we have a gradient because we have exactly one supporting hyperplane. Here we have multiple. We can have a set of hyperplanes that supports the function. So we will collect all their slopes as a set of subdifferential. So the formal definition is through this inequality. We say G is a subdifferential of f at x if the following inequality holds for n in z. This is exactly how we defined convexity in the previous lectures. Basically, this inequality says that on the left-hand side, fz is this function graph. Right, this fz is your function. On the right-hand side is a linear function in z. The right-hand side is linear in z. So the right-hand side is a hyperplane. It's a hyperplane that goes through this point and supports your function. Okay, and the slope of this hyperplane is this g, right? This slope is called the subgradient of f. And for a function, it may happen that at a single point x, multiple g's, multiple subgradients may exist. So we will collect the set of all subgradients of f at x. Just collect all the possible subgradients. We call it the subdifferential of f at x, and we denote it by using this notation, partial derivative notation. Right. So in this case, all these supporting lines all these supporting lines, their slope forms the subdifferential, the set of the subdifferential. And you can see if a function is differentiable, then the subdifferential is simply the gradient, because we just have a single supporting line at every point. For example, in this one-dimensional example, fx equals to the absolute value of x. So we have this graph of this function. So one-dimensional function. Now, what is the subdifferential of this function? Well, if x is less than or greater than 0, okay, like on the left or on the right-hand side, the function is differentiable, right? The only non-differentiable point is at the original point. Right? So in these two cases, the subdifferential is simply the derivative. So if x is less than 0, okay, the function is differentiable there. So the subdifferential is simply the derivative, which is -1. If x is bigger than 0, function is going up, so the derivative, the subdifferential is the derivative, which is +1. Now, what happened at this original point? Well, you just need to find out all the possible supporting lines, right? So you see, all the line segments within this area are supporting this function graph, right? So all the lines within this area, this is like between positive 45 degrees to negative 45 degrees, right? All the lines within this whose slope is between positive 45 and negative 45 degrees is supporting the function graph. So the subdifferential, so the slope of all these lines form the subdifferential. Okay. So it is a set between -1 and 1. Right? Because positive 45 degrees has slope 1, negative 45 degrees has slope -1. Right? So the subdifferential at x equal to 0 is between -1 and 1. So you can sort of interpret this as at point 0, any the derivative at point 0, right, is anything between 0, is anything between -1 and 1. It can be viewed as a proper, the kind of derivative or subderivative. So this would be the subdifferential plot, right? Less than 0 is just the -1, so it's a horizontal line. Bigger than 0 is just the +1, and at 0 it is this entire vertical line. Okay? From -1 to 1, any number between -1. If we go to high dimension, now this is x absolute value of x. This is like the norm of x of a one-dimensional variable. If we go to high dimension, we can also follow the subdifferential definition. So let fx be defined as the norm of x for any norm. for any norm. Here we did not specify the norm. Could be L2 norm, could be L1 norm, could be infinity norm, could be any LP norm. Okay. Then the subdifferential of f at 0, this set is basically contains all the vectors G whose dual norm is less than 1. Okay, let's look at this. The subdifferential of f at 0 basically contains all the vectors G whose dual norm is less than 1. Now, what is the dual norm? The dual norm is a norm it's like a norm connected to the, we call this, if you have every norm has a dual norm. Okay, they are forming a pair of norms in the space. And this dual norm is defined in this way. Okay, so once you specify this primal norm, we can have a corresponding dual norm. In mathematics, people care about this symmetry, this type of symmetry in space. So the dual norm is defined through this variational optimization problem. Is to look at all the vectors Z that has whose norm is less than 1, and has the highest correlation with your vector X, with the vector X. We call this the dual norm of X. But you can just understand it as it is another norm. Yeah, for example, LP and LQ, they form a primal dual pair if 1 over P plus 1 over Q equals to 1. Oh, I think it should be bigger than 1. For example, PQ, if you choose P equals to 2, then Q equals to 2, which means L2 norm and itself forms a primal dual pair. So the L2 norm is the dual of L2 norm itself. If you choose P equals to 1, then Q is going to be infinity. Now this means the dual of L1 norm is L infinity norm. Okay. And yeah, but this is how we define the dual norms. Okay. And we can actually prove this result just by checking the original definition of subdifferential. Okay. If G is the subdifferential of f at 0, then for n in Z, this inequality must hold. And 0 is the point we are talking about, and G is the subdifferential at that point. Now, then for n in Z, this inequality must hold. If you rearrange this inequality, F0, this is a norm. F0 is simply 0. But this is simply 0. And then this is a dot product. Fz is simply norm of Z. Okay, just plug it in. Then you have this dot product is less than Z. So this is like for all the Z's. So G is a subdifferential if for all the Z's, this inequality holds. And for the dot product, we know by Cauchy-Schwarz inequality, it is less than or equal to G, the dual norm of G multiplied by the norm of Z. But this is again, it's the most general form of Cauchy-Schwarz inequality. And then you can see, as long as this guy is less than 1, we are guaranteed that this product will be less than or equal to the right-hand side. So that's why we require this. That's why that is where this condition comes from. By this Cauchy-Schwarz inequality, this dual norm of G must be less than or equal to 1. For example, if you consider L1 norm here, then the subdifferential of L1 norm at 0 is simply what is all the vectors whose infinity norm is less than 1. Okay, so all the vectors whose infinity norm less than 1. And this L1 norm, right, it generalizes this example. This is a simple example in 1 dimension. But if we consider a high dimensional vector, we can consider its L1 norm.
Can you give us a little bit more background on dual norms? Like, why are we using them, and how do they relate to the subgradients?
Right. So they are not directly related to they are related to subgradients of norms. Yeah, but they are not directly related to subgradients of functions. If you consider a function of norm, then it is related to the dual norm. Yeah, for example, yeah, because in this proof, okay, let's look at this proof. If your function is a norm, now this is a special function. Now we are talking about subgradients of functions, right? But in this example, we are talking about functions of norms, right? We are consider fx that is the norm of x, but x is certain norm. For these type of functions, the subgradient is highly related to its dual norm. Why? Because if you follow the definition of subgradient, to calculate a subgradient G, in the end, okay, plug in everything, we need to find a G such that for all the Z, this inequality holds. And this is highly related to this definition. Because this definition is looking at the maximum dot product, right? Well, this Z is less than 1 as the norm less than 1. So these two, they look similar to each other. So this is why the dual norm is introduced. And the reason that the dual norm is involved is due to Cauchy-Schwarz. The left-hand side, okay. Yeah, so the left-hand side is bounded by dual norm of G times norm of Z. Okay. For example, if you put L1 norm here, then this is gonna be infinity norm. This is one form of Cauchy-Schwarz. 1 infinity, they satisfy this condition. Right. Or you can say 2 and 2. This is like a more general form that covers all these cases. Well, if you specify an abstract norm, then this is going to be the dual of that norm. Okay. And the dual norm is defined in this way. But you don't have to remember this definition. You just need to remember these concrete examples. 1 and infinity, 2 and 2, they form a primal dual pair. But this is just a more general way to summarize all these different scenarios. So if this is a norm, this is going to be the dual of that norm. This works for any arbitrary G and Z, and any two vectors in the norm space. This inequality will hold. But yeah, but here we are going to look at all the Z's. We need to find a inequality. We need to make sure this is hold for all the Z's. So if we consider all the Z's, then we can always choose a Z such that this Cauchy-Schwarz inequality achieves equality. We can always find a Z that achieves the equality. And that is the maximum value that the dot product can take. So you can say that the soup of Z is just this guy. The soup of this dot product is the dual norm of G times the norm of Z. Okay. Therefore, in order to satisfy this inequality, we just need to make sure the dual norm of G is less than 1. If this is less than 1, then this is less than norm of Z. Okay. So it is connected to the dual norm through this Cauchy-Schwarz inequality. A very interesting connection. The connection comes from the Cauchy-Schwarz inequality. In the definition of subdifferential, we have this inner product structure. But this structure by Cauchy-Schwarz is connected to the dual norm. So that's where the dual norm comes into play in this subdifferential factorization, okay, when these functions are norms. Yeah, and and dual norm is a very useful definition because you see for the same inner dot product, I can control it using different pairs of norms. I can do 2 and 2. This is what we are familiar with. The most standard Cauchy-Schwarz inequality, 2 and 2. We can also do infinity 1 or 1 infinity. Okay. It's more flexible. And this is a more useful example. We're talking about a maximum of 2 functions. Okay. Say you have this red is 1 function. This yellow is another quadratic function. Now you consider the maximum of these 2. So you pick this blue segments. These are the pairwise maximum of these 2 functions. for such a function, well, f1 and f2 are differentiable, and these two are differentiable, right? Because you can, in this example, in this figure, right, this is one quadratic curve, this is another quadratic curve, and they are intersecting. And now you pick the two upper parts. They form the maximum function. And then the subdifferential of this function, you can see that this part is differentiable, this line is differentiable, but this point is not differentiable because the slope doesn't match at that point. Right? So if f1 is bigger than f2, meaning that the red is on top of yellow, that corresponds to this part. But if f1 is bigger than f2, then the derivative is simply f1, it's differentiable. Otherwise, the derivative is f2, it's the left part. Okay? But when they match each other at this intersection point, it is non-differentiable, so we talk about subdifferential. Right? And at that point, the subdifferential you can see from this figure is like anything between these two tangent curves could serve as a subdifferential. So it is between these two derivatives. And this is the subdifferential plot. So at this non-differentiable point, there's a vertical line. So anything within this vertical line segment is a subdifferential. And we have some basic rules for calculating the subdifferentials, just like the derivatives. They satisfy this very simple. They're very intuitive. The scaling, summation, these are the same as derivatives. So, yeah, maybe look at one example. Well, fx is the L1 norm of x, which is the sum of all the absolute values of all the coordinates. And we call fix, we define fix to be the absolute value of the ith coordinate. We define this function. Then fx is the summation of all the fix, right? So fx is summation of fix. Then we can utilize this rule, this summation. We just need to figure out the individual subdifferentials and then kind of sum them up. So for every fix, we can derive the subdifferential is derived as follows. It's very similar to the subdifferential of a one-dimensional case, right? If it's not zero, then it's the sign of xi. Right? If xi is positive, then it's 1. Otherwise, it's -1. But we need to multiply a standard, a basis vector ei, because this is in the high dimensional space. If at this 0 point, it is not differentiable. So we talk about subdifferential. The subdifferential is anything between -1 to 1. We have shown in the previous example. But again, here we need to multiply by the basis vector, because this x is in a high dimensional space. So then we just sum them up over I. Just sum them up over I. And here, we can simply do the following. We can just sum over all the i's, and here for all those i's, well, xi is non-zero. I use this rule. Follow the top part of this subdifferential factorization. For those i's whose xi equal to 0, I can pick anything between -1 to 1. So I can simply pick 0. If I pick 0, then I don't need to worry about those coordinates. So in the end, this is a proper subdifferential of this function f. And we have more examples, which I will not go over, but they are pretty similar to the derivatives. Right? In derivative, we have similar affine transformation rule. If H is F composite with an affine transformation, then we know if it's differentiable, then the derivative is A transpose the derivative of F, right? But here it also applies to subdifferential. Okay? Also applies to subdifferential. It's the same. And this is just another example where this L1 norm is as an affine transformation inside. So you just apply that rule. And I will not go into details. So you have A transpose. You have an additional A transpose outside. And there are some other chain rules and the composition rules which are pretty similar to those rules for derivatives. And we have seen them in the lecture 0. So I will not go over them in detail, but we probably won't need them in this course. But this is good to have as a reference. If F is convex, G is differentiable, non-decreasing and convex, then G composite with F. This function, this compositional function, the subdifferential can be characterized as follows. Yeah. One thing I want to talk about is this pointwise maximum and the pointwise supremum function, because many functions takes this form. Okay. So if fx is given in a pointwise maximum form, it's the maximum among k different functions. Then the subdifferential of fx is given as the following set. Okay, let's look at this set. Inside, let's first look at this set. This is the subdifferential of fix, right? The subdifferential of fix. Well, this fi, at this point x, this fi achieves the maximum, right? So what you do is this. Fix a point x, okay, and then check at this point which fi achieves this value, which fi achieves that maximum value. Maybe some of them are smaller, some of them are higher, right? But the one that achieves the maximum value, we call them the active functions. Right? At this point, some of these functions are activated, right? In this sense, right? Some of them are equals to the happen to have the maximum value among all these different functions. for those active functions, we consider their subdifferential. Okay, so each active function at this point has a subdifferential, which is a set. Then we take the union of these sets. Okay, maybe this active function 1 has a subdifferential, active function 2 has another subdifferential. These are two different sets. Take their union, put them together. But once we union them, it may not be a convex set. So we consider the convex hull of this union. Right. For example, this could be subdifferential of f1x, the set of subdifferential of f1x. This could be f4x. Suppose f1 and f4 are active at x. These two functions are active at x. Now these are the subdifferentials. Take their union. Now, in the end, you need to consider their what convex hull. Just to consider the convex hull of these two sets. Everything within this convex hull is a subdifferential of fx. And this pointwise supremums is exactly the same thing. Yeah, nothing different. Exactly the same thing. But yeah, in the end, there's a closure outside. But okay, if you're not familiar with this operation, we don't have to worry about that. But they look pretty similar, right? Because this is maximum among finite number of functions. This is supremum. But you can see at least the subdifferential of all the active functions at this point, they are proper subdifferentials for this fx. Okay. So at least the points within these two sets, they are proper subdifferentials. But this result says that it can be even bigger, as long as it is within the convex hull of the union of these sets. Yeah, and this is very useful. For example, we can use that to consider the pointwise maximum linear functions. This function fx is a piecewise linear function. It's defined as a maximum over a bunch of linear functions. It's pointwise maximum, and you can follow that subdifferential rule to calculate the subdifferential. So for each of them, the subdifferential is simply AI, right? It's a derivative, because for each of them, it is differentiable. So the subdifferential is simply AI. So we just need to consider those AJs. Well, those J's are active. Those active linear functions, and consider their coefficients, their slope, AJs. Another example is the infinity norm. If fx is the L infinity norm of x, by definition, it is the maximum absolute value among all the coordinates, right? Again, this is a maximum form. It's a maximum form, pointwise maximum. So you can apply that subdifferential rule to compute the subdifferential of this function. It is basically look at those active coordinates, okay, those coordinates that achieve the maximum value, and then consider its sign multiplied by this basis factor. This is a proper subdifferential of this function. So this activation needs to be, you need to check this activation condition. And this eigenvalue, maximum eigenvalue of matrices, we have seen in the previous examples that eigenvalue of a matrix is related to can be rewritten in a supremum form. Fx is this, is x1a1 x plus xn so it's a linear combination of a1 and an, well the coefficients are given by x. Okay, once you do this linear combination, and then you consider the maximum eigenvalue of this entire combined matrix. Well, these AIs, they are real symmetric matrices, so we can see so it has eigenvalues. Okay, this is a function, right? Given an x, the maximum eigenvalue will be fixed, will be given, depends on a1 up to an. Okay, so we rewrite this maximum eigenvalue into this variational form. Okay, this is a very useful variational characterization of eigenvalues. It's basically y transpose this big matrix times y. Well, we take the supremum over all the y's that has unit L2 norm. And we look for all the y's that has unit norm that achieves the maximum, the supremum value of this problem. So this equals to the singular maximum eigenvalue. Then this can be regarded as what? As supremum. Fx is written as a supremum of functions, right? So we can use that as formula to compute the subdifferential. Yeah. Then apparently taking y as the leading eigenvector of this matrix. Okay. So consider the leading eigenvector of this matrix. That eigenvector achieves the supremum value of this problem because it is the leading eigenvector. So it must maximize this expression. Okay. So taking that y as the leading eigenvector, and then this forms a proper subdifferential. Because once you take gradient with regard to x, it's just y transpose a1 times y. This is a scalar. Is this scalar times x1? This scalar times xn. So these are all scalars. And you put them together, you can get a proper subdifferential. Well, this y is the leading eigenvector. Okay. This is to satisfy the active condition, right? This y, this leading eigenvector, achieves that supremum. Right? We need to check this activation condition. So it's here. Yeah. You need to achieve that supremum value. In this case, the leading eigenvector achieves that. Okay, I think we are 3 minutes over. So I will stop here. And yeah, next time we'll continue to talk about another example on the nuclear node. We have a big project that is related to the nuclear node. So yeah, we'll get into this. So I'll see you on Thursday.